Hello all, hope you are doing good. I welcome you all to the fifth lecture of this course EE614. The last time we met, we discussed about periodic arrangements of atoms, the consequences of such arrangements, the emergence of band gap, and so forth. We touched upon an important concept called the density of states. But then we did not dwell further into this, and that will be the motivation for today's lecture. So we discussed that if we have a periodic one-dimensional array, we saw that you have bands, right? You have, let us say, let me draw like this, right? So right, you have something like this. When you are close to the Brillouin zone, and then you have something like this. And this continues further. And this is what we call as the energy gap. Right? While we saw that this relationship is basically these lines, right? They are basically E versus K, and they come about because we considered the electrons to be in the form of block waves, e power I k dot r, u of r, where u is the periodicity of lattice. And when you have such a description, you can describe the energy wave vector relationship to be h bar square k square by 2 m star, where m star is the effective mass, right? Which is not, when m is equal to m naught, that's a free electron mass, which is a normal parabola. And when we have this periodic lattice, we modulate it with some mass called the m star, which is called as the effective mass. We will deal more about the effective mass in some time, but as of now, let's say it's just an assumption, or it's a gross approximation for the mass of this electron in a periodic lattice. Right? The important question now is how many electrons can be there in any of these bands. Let us take this band or this band. How many electrons can there be? Can there be infinite? If there is infinite, you can actually see that there can be only one band, right? All the electrons in this solid will be in one band, and no further bands are actually necessary. That is not the case, right? So there can be only finite number of electrons in the band. So we will derive this number, what this finite number has to be, and why there has to be a finite number of such states, and we will describe about various particles and how much does it come out to be, and so on and so forth in this lecture. Right? So let us once again go back to this particular definition of block, where psi is the wave function of an electron, and we are trying to describe this wave function in a solid, right? And we will take a simplest solid of a cube, something of this sort, of say of length L. If we assume that this wave function dies outside this cube, right? If it dies sharply outside this cube, you can easily see that because these are traveling waves, let's say something at the center, it is going to travel here on both ends, and it dies at the edge, then there is bound to be some reflection, right? Because if you think about continuity at the end, if one guy dies on the other side, it has to be reflected completely. And when the wave functions are completely reflected, you will have standing waves, which is not good because you do not have standing waves in normal material, right? So the approximation to deal with such a problem is what is called as von Karman. I forgot the spelling, it is BVK, okay, approximation, which says that consider like you have a super large ring of this material, and whatever that we are considering is somewhere in between at the center here, right? This is LL, such that you have many such samples surrounding this. so that at any point at the interface of this particular sample, the condition is just the same as if you started at 0 here. Let's say this is L. At any edge, you have another sample P such that you just start back. So it is something sort of a periodic condition that we previously saw. Right? Of course, remember, this is not a unit cell. A unit cell is still some small portion here. Let us say that you have Ni unit cell in this direction, N1 unit cell in this direction, N2 unit cell in this direction, and N3 number of unit cells in this direction. So basically you have N1, N2, and N3 in each of these things. Right? So under this particular approximation, which is called as Born-von Karman approximation, you have the psi of R is equal to psi of R plus Ni-Ai, where Ai's are actually the lattice vectors in real space, right? So we know about this. Ni-Ai will reach you from here to here, N1, A1, and N2, A2 will go in the vertical direction, and N3, A3 in the vertical, right? In the other, all the three directions. Right? So if we have something like this and we substitute our previous block wave, we know that psi of R plus Ni Ai is e power I k dot R plus Ni Ai u of R plus Ni. Now we know this u to be a periodic function. That's the basic definition. So this is basically u of R, right? And this is e power I Ni k dot Ai u of R. And this k is a reciprocal space vector, right? And we saw how this k has to be written, right? In the normal sense, you know the definition of a reciprocal space vector, right? K is, let us say, ki bi. When you have something like this, then this definition can be rewritten as e power I 2 pi ki Ni. And if this has to be the same as this condition into psi of R, this is psi of R. If this condition has to be true, then we know that this has to be 1. For this to be 1, you know that ki Ni ki is equal to some integer m, right? Now we are looking for the smallest value of ki, right? Because if you see in this band structure, each of these things are this is basically k, right? Each of these things are k's, and we are trying to see what is the smallest value of ki that we can define. If the smallest value is if 0, then you have infinite number of k's. But we just see that because of this periodic condition, this ki cannot be a non-integer, or this m has to be an integer. So if, let us say, we take the simplest and the first integer to be 1, of course the non-trivial 0 is 0 anyways, the smallest ki will turn out to be n by ni in one direction, right? And we know that this is a 3-dimensional thing. So the del k in 3 dimension, and Ai's being the various reciprocal lattice vectors, and Ai's being the real space lattice vectors, and Bi to be reciprocal lattice vectors, and k is equal to m is 1, right? 1 by ni. Ki to be 1 by ni. The smallest vector in the B1 direction will be B1 by n1, right? And B2 by n2 cross B3 by n3. This will be the smallest volume in the K space, right? Well, B1, B2, and B3 are the reciprocal lattice vectors. This comes from standard geometry. Right? These things are constant. We have 1 by n1, n2, n3. And B1 dot, this is the reciprocal lattice unit cell, which we can very easily represent by nu. Nu is a real space unit cell, remember. nu is the volume of the real space unit cell, and we know this is a relation from our previous descriptions. And this n1 into n2 into n3 is the number of unit cells, right? And this will turn out to be 2 pi cube by capital V, where V is the volume of the sample that we considered, right? Because if I have n1 into n2 into n3 of number of unit cells we have, that will give me the entire sample volume, right? So the smallest k vector that I can define is inversely proportional to the size of the sample. Now, in hindsight, you can always think, yeah, this is obvious, right? The larger the sample I have, the larger number of electrons that I have. So basically, I should have smaller the resolution in K to accommodate all the electrons in the sample, right? So basically, this is the definition of. So if we take this particular band structure, I'm saying this del K that you can consider is 2 pi cube by V, the volume of the lattice. Right? Now we know how much each the smallest resolution in K, we can define what is called as the density of states. And this is defined as, let us say, G, right? It's a function of energy. We choose energy because it is equivalent to choosing a K. Right? All this time we have K as the x-axis, so we all like to talk about K, but in general conventional sense, people like to talk about energy. There is no particular reason to choose energy because energy and K are related by this very simple relation here, but people just generally like to go about defining the number of states per unit energy is called the density of states. So number of states per unit energy per unit volume, so that you don't care about how much bigger sample that we take. So this is the basic definition of density of states. Let us forget the volume for now. We will get back to this final definition. So just the number of states per unit energy is, so number of states per energy is basically, let us say, dN by dE, right? Now we have all these things in K, right? So basically you can redefine this by dN by dK into dK by dE. And we know the dK by dE relationship from here, dE by dK, right? So dE by dK will turn out to be hk by h bar h squared k by 2m star, right? So h bar squared k by 2m star. And now we have to find dN by dE. For this, let's assume some sphere, because we are still in a 3D lattice. Let us consider a sphere of radius k, some k, right? So how many, we saw the resolution, so we are now trying to count the number of states. So this n will turn out to be, for any particular sphere of volume k, is 4 by 3 pi k cube, right, divided by the resolution that we just now found, which is 2 pi cube by volume. And we are talking about let's keep it like this, right? So with this given, now it's very easy for me to find dN by dK, right? It is 4 pi k square by 2 pi cube into V. This is capital V. Now if I use this definition to find the total density of states, is basically dN by dE into dN by dK into dK by dE all of them divided by V will give me the actual density of states, and this for 3D space will come out to be root 2 m star power 3 by 2 by pi square h bar cube root e. So this is a pretty important result, in the sense that the number of states, of course, please remember this is also accounted for the spin. So typically each energy level can have 2 spins. We will go into the details about these things, why it is so and such, but each energy level can have 2 spins. So this particular number is the number of electrons that you can have per unit energy. And what we are trying to say is it looks like this. If this is G and this is energy, it goes like this, derivation of root E, right? Which should not be very surprising, given that the energy is quadratic in K, and K is the number of states that you can have. So this counts to be not so new. But one can also derive the same density of states in the cases where we do not consider a sphere, as we have done here. So here this is a sphere in K space, right? This is Kx, Ky and Kz. We think that the reciprocal lattice is a cube, is a 3-dimensional space. Now instead of that, if we assume that the reciprocal lattice is a 2D system, such that you have only Kx and Ky, how will this change? This is a question for you to try. It's a problem as an homework. The only difference would be in your dn by de, which is your n is, instead of 4 by 3 pi k cube, it has to be pi k square, right? Divided by the same thing. But instead of this being a 2D space, it will be instead of a 3D volume, it will be a 2D area. So I would like you to try this. Calculate G of E for a 2D lattice having a K space like this, and an 1D lattice which is a line minus K plus K, and you can calculate what is the del K for such situation. So what is G of E for a 1D lattice and a 2D lattice? So this is a problem for you to try. So now that we have a reasonable a number which is called as a density of states, which tells you how many states that you can possibly have, we have to go and see how many that do we have in real space, right? In reality, how much do we have in under all possible conditions? What happens if I change the temperature? What happens if I change the doping, and so on? We will go into all these things, right? So the next important concept that we will deal today is called as carrier statistics. This is what determines how many carriers that are actually there at any given condition. An important aspect when you talk about carrier statistics is called as indistinguishability. So you will come about this particular term in many places. So we will just give a very brief introduction to this. We will not go very deep into this because it is beyond the scope of this course, but it is still necessary for you to have a feel for what people mean when they say two things are indistinguishable. So what they mean is, let us say that I have a state here and I have another state here, right? And this state has an electron with a particular spin, right? And I have another electron with this particular same spin, right? Now when you have these two states, there is no way to tell which electron is there in which state. Let us say this state is tagged R1, this state is tagged R2, and this is psi1 and this is psi2. So when something is like this, and another situation where you have, let us say this like this, right? In the second case, it is clearly distinguishable because these two things are not really the same, but in the first case it is actually indistinguishable, right? You do not know when you actually change these things. However, while I have actually given you this example, in reality it does not happen to be like this, because there is always a random distribution of spins and the electrons and so forth. So spins is not an ideal thing to have indistinguishability about, but this is just an example that I just gave for now. But in practice or in quantum mechanics, indistinguishability means something that you can measure. Here we actually see it, but it's something that you can measure. You can measure velocity and stuff. And what you can measure is typically represented as a wave function, as we saw before. Right? So if this is the wave function of this particular configuration of these two electrons, right? So basically the square is what you can anyway measure. And if this is true, R2, R1, then we say that these two configurations are indistinguishable. That is, I swap what was in R1 to R2. So basically this means I am swapping. This can be achieved in two ways. If psi of R1, R2 is equal to the psi of R2, R1, this can be true. Or if psi of R1, R2 is equal to minus psi of R2, R1. Under both these situations, this particular equation is true. Right? That means that under both these situations, this particular arrangement or configuration is indistinguishable. Under such situations, particles which obey this particular relation are called bosons, and particles which obey this particular relationship are called fermions. There are only two class of particles in this entire world, because these are the only two ways in which two particles or two configurations can be indistinguishable, right? So there are these two kind of particles. Bosons examples are photons, gluons, and so on and so forth. And fermions, the electrons. You have other composite particles called neutrons, protons, and so forth. All of these guys are still fermions. Fermions have this particular anti-symmetrization behavior, right? So when you write the complete waveform, if I want to write this particular psi, right, in the normalized form, I write the bosons as 1 by root 2 because it is normalized, right? Because everywhere it has to be 1. I have psi 1 R1, psi 2 R2 plus psi 1 R2, psi 2 R1. This is the way a normalized boson wave function is written for two particles, and the same thing for fermions is written like this. You can see why this will satisfy this equation and this will satisfy this equation. Also, this also can explain why Pauli's exclusion principle is true, right? If you have two electrons whose wave function is the same, a wave function is a combination of all the quantum numbers that you can have, right? If two wave functions are exactly, if two particles have exactly same wave function, then you can see that psi 1 of R1 is equal to psi 2 of R1, and if psi 2 of R2 is same as psi 1 of R1, you can see that this particular equation goes to 0. So basically this configuration is always will have 0 wave function, 0 combination wave function, and hence no two fermions can have the same wave function and cannot have all the same quantum numbers, right? So basically it is this particular relationship or this particular way in which they obey the indistinguishability condition gives you this Pauli's exclusion principle. Also, it was further shown by Pauli that particles which are fermions have or have half integer spins, and particles who are bosons have full integer spins. With that given, or with that brief what to say treatment of these particles, we go into the actual statistics which can actually be derived, but we won't once again derive these expressions. We'll just give it for you. You can determine how they, at any given temperature, you can determine how they are distributed in the energy levels. This is given by what is called as Fermi Dirac distributions. What it gives you is, if you have some n states with this energy level increasing, right, and each energy has, so basically his energy level has this del E has some degeneracy Ni, right? This distribution just tells you what is the average number of states of this DE are occupied, right? So this Ni, this average number of states which are occupied, which is typically represented by f of E for fermions, is given by 1 plus E power E minus mu by kT. You can see that the average number of states which are occupied in any energy level E is proportional to the actual energy level, a component called the chemical potential mu, and the temperature T. Right? We will define this mu very quickly, but this is what will actually determine the occupancy of fermions in a particular system. Right. So let us try to have a feel for this particular Fermi-Dirac distribution, and then we'll see its relevance in solid state physics or in semiconductors and so forth. If I plot this Fermi level or this Fermi function like this, and this is energy as we have previously plotted, and this is the Fermi function. If we plot this particular function for 0 temperature, it will look like this. It is discontinuous at some energy level, right? And below this energy level, all the values are 1, and above this energy level, all the values are 0. It comes out to be like this. So this value is 1, this is 0. This energy level is what is called as the Fermi energy. So definition of Fermi energy is the energy level up to which all the states are occupied at 0 Kelvin. Right? That's the definition of Fermi energy. And this is what we have here. And this mu is the Fermi energy, right? And as I increase the temperature, this discontinuity slowly disappears. It starts to smoothen out around the Fermi level. It turns out to be like this. 1 for some small increase in temperature, and for very large temperatures, it turns out to be like this. All the time, the probability at this energy level at any non-zero temperature turns out to be half. So this F at EF at is equal to 1 at 0 Kelvin, and at any other Kelvin it is half, right? Because it is discontinuous at 0 Kelvin. At any other temperature T not equal to 0, it is half. So with this introduction on the Fermi level, let us go and then deal with this relevance of this Fermi level and its aid in allowing us to calculate the carrier density at any given temperature in a semiconductor. So let us say that I have my density of states like this, right? So I have my valence band like this, I have the conduction band like this, right? Once again, this is energy and this is k vector for this particular drawing. And for the Fermi function, I also plot the Fermi function like this, right? And we saw that at 0 Kelvin the Fermi function should lie like this, right? So basically all these states are full, all these states are empty, and this is 1 in the case at 0 Kelvin, right? At any other temperature, it starts to smoothen out, right, such that you have some occupancy here and there are some states here which turn out to be vacant, right? And this happens because any electron which is here is excited from here to this particular state in the conduction band. That is the energy, the thermal energy that you see at 0 Kelvin, there is no energy for the electron to jump from the top of the valence band to the bottom of the conduction band, and all these states are completely full, right? This is very straightforward. As I increase temperature, some of the electrons can get the energy to be excited from the top of the valence band to the bottommost of the conduction band. And once you start populating this conduction band here, right, you start creating vacancies in these places, right? And these vacancies act as if they are positively charged, right? This is what we saw before. The reason for this is just the slope of this band, right? So we saw that the effective mass is inversely proportional to the slope of this particular curve, right? If we have d by dk to be a negative number, it will act as if it has a negative mass, and that's why they act as if they have a positive charge, right? And hence that's what we call as holes, right? Their holes are positively charged and then they have transport in the valence band, right? So basically at any given temperature, the Fermi function determines what is the relative population of electrons. So the population of electrons in the conduction band, so basically f of e gives the population of electrons in conduction band, probability of populating a state in conduction band, right? And 1 minus f of e is the probability of a state being empty in the valence band, right? F of e is it being occupied and 1 minus f of e is the probability that it is empty. With this definition, you can calculate the number of electrons in the conduction band, right? Is basically the density of each energy level G of E, right, into the probability of it being occupied. And this has to go over all possible energies, right? This will give you all the possible states which were occupied on all the electrons that are present in the conduction band. And if we have enough number of states, then this can be converted to be an integral G of E, F of E, and D, where D is the small change, and this of course comes from at least should be larger than the del K that we previously saw, right? And this should be bottom of the conduction band to infinity. I must let you know that this infinity is not true completely, because this band do not continue to infinity. We saw that at some point this will also flatten out, right? This will also lead to a band gap higher than this, but the Fermi function dies out so quickly, right? This can be almost taken to be true, because after a certain point your f of e is, let us say here f of e is almost 0. It does not matter how many states that you have above this particular point, right? So for all practical purposes we can take this one to be true. With this given, right, so this is here, Let's substitute our previous expression for the density of states in 3D and then see how we can come up with a simplified equation for the carrier density, right? So our previous let me pull out the expression. So which will be EC to infinity, we have root 2 m effective power 3 by 2 by pi square h bar cube, right? Root of E minus EC, and f of E is 1 by 1 plus E power E minus mu by kt d. This seems to be a complicated expression, but then it can be pretty easily simplified if you root 2 me power 3 by 2 pi square h bar cube, right? EC infinity root of E minus EC. If you assume that this particular term is much larger than 1, which is true if your Fermi level is much smaller than the energy under consideration, right? Which is true in many semiconductors, because let us say our semiconductors are like this. The Fermi level lies at the center, right, at some point, right? So this is the Fermi level, and the EC starts at the energy levels much larger than the temperature. So basically this is about greater than let's say 0.5 eV, right? The room temperature is about 26 milli electron volts. We have several times higher. So basically in all practical conditions, this one will be this expression will be much larger than 1. So you can simplify this to be e power mu minus E by kt, right? With this given, e power mu by kt is a constant, so you can mu by kt integral EC to infinity root of E minus EC e power minus E by kt d, right? Now you can do a change of variable. If we put E minus EC to be some other variable, right, you can bring out you can simplify this, right? So basically I'm not going to go into details, but you can simplify the entire thing to be equal to 2 into 2 pi me power kt 3 by 2 by h square, not h bar, sorry. This is an important point. It's not h bar but just h, right? So when you derive this, you have to see that it is till now we have been dealing with h bar and now it is h square into e power mu minus EC by kt. So this we simplify by writing this as NC f of EC, right? Once again we use the approximation that the exponent is much larger than 1 that we have done here, right? So basically what we are trying to say is, under the situation where the mu is, or the Fermi level is in the middle, close to the middle of the band gap, right, and it is much lower than the conduction band by several kts, which is called as a degenerate limit. Under such conditions, we know that the number of carriers is equivalent to an effective density of states, which is given by this particular formula. Effective density of states in the conduction band and the occupation probability of the conduction band. So we mean to say that you can approximate a semiconductor such that all the electrons that appear, right, just appear at the bottom of the conduction band, with whose occupation probability of is f of ec, and whose density is not the actual density of states but some approximate density of states called the effective density of states, which is called as CNC, which is given by the expression above. The same thing you can derive for holes, which will be P is equal to NB. Of course, it's 1 minus F of EB, right? So this will be the number of holes, and this will be the number of electrons in a degenerate semiconductor at any given temperature. And this NC and NV are obviously a function of temperature. And these Fermi functions are also function of temperature, right? So with this particular treatment, I stop here, and let's meet again. Thank you.